presentation, I will introduce the concept of page replacement algorithms and explain why it's important in virtual memory systems. So my name is Khadijatu Haidara. My student number is 210-208-906. And there are my teammates Umu Jara and Halimatu Sadia Isa Usman. So therefore, we're going to start with the introduction. Page replacement is essential in virtual memory systems. Page replacement is a key mechanism in virtual memory. It allows the system to decide basically which pages to keep in memory and which ones to remove when space is limited. For the second line, we have when a page fold occurs and no free frame is available, OS must select a page to evict. This means when the program needs data that is not currently in memory, we get a page fold, okay? If the memory is already full, the operating system must choose one page to evict and replace with the new one. It's as simple as that. Now we have the third line. Replacement policy directly affects page fault rate, I/O overhead, system throughput. That basically means that the choice of replacement algorithm has a strong impact on performance, basically. It influences the number of page faults, how much I/O the system has to do, and also how fast the system runs. So for the last line, we have the goal, compare classical and modern replacement algorithms. That basically means that in this study we're doing right now, our goal is to compare both classical algorithms like, for example, LRU and modern ones like ARC or Clock Pro to see how they perform under different workloads. So that was it for the introduction. I'm going to move to the next slide. So here we have the background. Before looking at the results, here is some background information about virtual memory and page folds. So we have virtual address, space is larger than physical memory, missing pages, page fold, disk operations, and minimizing page folds equals to a better performance, as you see on the screen. And we have two categories of policy. We have the local replacement and the global replacement. So that basically sums it up by itself. So I'm gonna take them one by one. I'm trying to be quick. So the virtual address space is larger than physical memory. That means that programs see a very large address space, but the actual physical memory is much smaller. Virtual memory bridges this gap. So for the missing page part, it basically means that when the needed page is not in memory, the CPU triggers a page fault and the system must load the page from disk, which is quite slow. Also, we have minimizing page fault equals to better performance. This means that because disk access is really expensive, reducing page fault directly improves performance. Now we have two categories of policies, local and global replacement. So replacement algorithms can be classified as local or global. Local means each process manages its own frames. Global means all processes share common pools. So therefore, we're gonna move to the next slide, and it's, I believe, Halima's turn. So I'm gonna move to the next slide for her.
Okay, now let's move on to the classical algorithms. We have the FIFO, optimal OPT, LRU, and clock. So I'm gonna explain each of them like in a really quick way. Firstly, FIFO removes the oldest page in memory. It is very simple to implement, but it may remove pages that we still need. It also suffers from Bailey-Day's anomaly, where adding more memory increases page faults. And after that, we have the optimal OPT. and it replaces or removes the page that will be used furthest in the future. It gives the best possible performance, and we use it as a benchmark, but it cannot be used in real systems because we cannot predict the future. We also have the LRU, which removes the page that has not been used for the longest time. It usually performs very well and does not show belly days anomaly. Implementing exact LRU is very expensive because we must track the exact usage order. And finally, we have the clock, which is a practical approximation of LRU. It uses a reference bit and a circular scan to decide which page to remove. It keeps a good balance of performance and a low cost, which makes it very popular in real operating systems. To the next slide, we have the adaptive and modern algorithms. As workloads became more complex, classical algorithms were not always enough. So modern algorithms try to combine recency and frequency of page usage. Firstly, we have the aging, not frequently used. These approaches are used to counter to measure how often and how recently pages are accessed. Then we have the Clock Pro, which improves clock by separating hot pages and cold pages. It also tracks pages that were recently evicted. And the ARC, which is the adaptive replacement cache, is one of the most efficient modern algorithms. It then dynamically balances recency and frequency using multiple lists. ARC adapts automatically to workload changes and often outperforms LRU and clock in mixed scenarios. So that is all for this slide. We can move on to the next one. Thank you.
Performance comparison. Now I will compare the algorithm. Optimal is the best one. It has the low page fault because it shows the page is very late in the future. LRE is usually better than FIFO, especially in real programs. FIFO is simple, but sometimes it works very bad. More memory equal more page faults. This is called Belady's anomaly. Clock is also like LRU, but it is easier and cheaper to use. Modern algorithms like ARC and Clock Pro are even better. They understand recent and frequent page use. Next slide. Practical use in operating system. In real computers, the system must choose the best balance. Many operating system is closed because it is fast and simple. Big server with a lot of memory can use IRC or Clock Pro. They give better performance than the workload change. So this is my presentation. Thank you.
This concludes a comparative performance study. Now here we have 5 lines. We're going to take each of them to conclude the presentation. First, we have no algorithm is best for all workloads. That basically means that there's no single replacement algorithm that works perfectly in every situation. It might work in a situation and not work for another one, which is perfectly normal. We have OPT equals theoretical reference only. That means that OPT represents the ideal behavior, what's supposed to be done, but it cannot be implemented in real systems. It is only used as a benchmark. That's pretty self-explanatory. Now we have LRU and clock equal the good real world balance. That's pretty much self-explanatory, but it basically means that algorithm like LRU and clock offer a good compromise between performances and implementation cost. Simple. Arc and Clock Pro equal best adaptable performance. That basically means that modern algorithms such as ARC and Clock Pro adapts better to changing workloads and often give the best performance. And then we have the last part, understanding trade-offs key to efficient systems. That means that each algorithm has strengths and weaknesses, which is normal for anything in general. Understanding this trade-off helps system designer choose the most efficient approach. So that was the conclusion to our presentation. And this is our team members. I am Khadijatu, and there is Halima and Umu and our student numbers. And thank you for your attention.